what we did in 4.3 was to look at Riemann sums, rectangles, and we narrowed the width of the base of those rectangles down and down and down and down by increasing n, the number of those rectangles, and took a limit going to infinity. That's basically, in a nutshell, what we did. And we said that limit is the area under a curve. All right, we're going to do an easier way here. They're calling this the fundamental theorem of calculus. Technically, you'll see that in some books. Technically, it's the fundamental theorem of calculus, the second one. You'll see why I'm saying that in just a minute. Nothing to quibble over. I mean, it doesn't matter. But this is saying, all right, we've got an interval, a to b. We've got some function, f of x. Got to pay attention to this part. It's saying if capital F is an antiderivative, meaning we integrate that, then you can get that the area under the curve just by saying capital F of B minus capital F of A. This is neat. Watch what that means. Okay, so if you can find an antiderivative of F, here's what you do. Notice the notation here. This little symbol right here is saying I'm evaluating from A to B. And we've looked at that before. It's been a long time. I'm breaking this up into boxes. It's got kind of 4 parts. First of all, your original integral here. And then you're telling me, what are you integrating? So I've got x to the 4th over 4. So we're just getting an antiderivative for it. Then you're plugging in numbers. So look what you do. You take the value for b up here on top first. So I'm saying 3 to the 4th divided by 4 minus 1 to the 4th divided by 4. Well, I got the 3 and the 1 from here, actually, from our integral. You work those out, and you get a final answer.
Why don't we replace that with 3 and not 4 with 1? Why don't we replace x with 3 but not 4 with 1?
Because I'm going from 1 to 3. So it's 3 to the 4th. My interval is 1 to 3.
And that just gives you
You with me? Okay, look. Our interval is going from 1 to 3. Look back at our original problem. It's going from 1 to 3. So wherever I see an x in this second part, I'm just plugging in 3. I'm glad you asked. Same way with the 1. And then you work that out, you just get an answer. That, in that short of a time, is what we spent sometimes 5 or 10 minutes on last time to work out with the rectangles. This is a big one. Notice the constant of integration drops out. Don't need it. And here's the reason why. It just more or less cancels out down here. So what's the takeaway? Well, big F is the antiderivative. Big F is the antiderivative.
It's like so much easier.
Tons. Okay, so let's work a couple. All right, so going from 1 to 2, we're integrating that.
So it'd be a 2 squared minus 1 squared minus 3?
So first thing I'm going to do is just write down my basic with the x's in it.
Oh, do we need the antiderivative?
That is the antiderivative there. So yeah, write it out. And then we're going to evaluate that from 1 to 2. You're good. Okay, so I start with the 2. So I'm going to plug 2 in every place I see x. And then I'm going to plug 1 in every place I see x. So each of those has 2 terms, notice. Where are you going to mess up? Well, the signs. You're going to not change a negative to a positive like on that second term when you should. At this point, it's just plug numbers in. All right, so simplify that a little bit. Combine like terms, if you will. They're all numbers, but I'm just combining things that look alike. So minus 6 plus 3 gives me the negative 3, and then I've got 8/3 minus 1/3. I changed the 3 to thirds. And so I'm getting this. That's a negative area. Can we have a negative area?
And if it's below, on graph below the x-axis or
Look at f of x. Look at f of x. Is there anything there that would lead us to think we might have a negative area going on? It's a parabola. That minus 3. What does that do to the vertex? Drops it down 3. So since we're going from 1 to 2, then that area is just negative. So yeah, we can have a negative area, but know how that interprets. It means it's just below the x-axis. Is all. All right, let's do another one. This is the fun part. So I've got 3 times the square root of x in my integral. So the first thing I'm going to do is just rewrite it and pull the 3 out. Yeah, like John said, I didn't really write it out with the variables in there. I should have, but I didn't.
It's just
Okay. So I plug 4 in, 4 to the 3 halves, divided by 3 halves, and same way with the 1. And I modify that a smidge. Thank you, sir. So notice on the bottom, I just flip that over and say, well, that's just 2/3 times 4 to the 3 halves. And how do you do that? Well, one way you could say, well, what's the square root of 4? That's 2, and then raise it to the 3rd power. That's where I'm getting the 8. And the 1s are easy. On the test, it'll be like the homework.
These are way easier.
These are kind of leading up to, but it's not going to get much harder. I mean, look at this. So I'll just get 14. So if you graph that and actually, kind of thought about it, you're not going to get 14, but you can see maybe where it came from. Without calculus, how would you do this? Those rectangle things. But that's part of calculus. So if you didn't want to do it this way, you could always go back to the way we did in 4-3. If you want to do that, then just get a hammer and start hitting yourself in the head.
We have an option most of the
No, you're going to do it like this.
No,
This is
will we be asked to do it the old way?
no. Well, on a test, yeah, just to see that you can. All right, last one. Oh boy, trig.
Secant squared is the derivative of tangent, correct?
Excellent. So I get my antiderivative here. And I did think to put it in terms of x this time. So we're going from 0 to pi over 4.
Isn't the tangent of 0 on the pi?
No, sir?
Okay, then it's just 0 there.
Okay, the tangent of pi over 4, if you do the left-hand trick, you realize the sine and cosine are the same at pi over 4. So it'd be something divided by the same something. So I'm just getting 1. So it's just 1. The area under that curve would just be 1 on that interval. I'd a whole lot rather do it this way than the way we did last time, given the choice. All right, let's move on. Mean value theorem.
Yay! I love this.
Boy, I am so glad. Okay, what is this saying? What is this saying? I know what it says in words and math. Imagine this curve right here. All right? I've got my interval going from A to B. That's the green lines. With me? So there's a C in there someplace.
That when multiplied by A minus B minus A.
No, okay, think about the geometry. What's B minus A? Is it a point or a length or an area or what? It's the length. It's a length, right? So it's B minus A is just this length right here. And then I've got some point C in there. This is saying there is a point C in there if we meet the conditions, if it's continuous on that closed interval. There is a point C, and up here is F of C, where it hits, where C would, that would be the point F of C. If I do this and draw a line straight across, what this is saying is the area of that stuff I have in red is equal to the area under the curve. That's what this means in geometrical context here. So there is some C out here, and we could find it if we wanted to, that if I take F of C as the height of that rectangle, if you will, and B minus A is the base of that rectangle, the area of the rectangle equals the area under the curve from A to B. And just reading that, it might not come across what that really means in a geometry sense. Okay, so let's look down here at the bottom. The average value of a function. Look at the curve I've got up there, f of x. Can that have an average value?
Yeah.
Down there at the bottom, that definition of the average value seems to imply that it could.
I mean, yeah, but if you do it without, if you try to solve without calculus, you're talking about every single
Point.
So
An infinite number of points.
Yep. I guess this might be easier than doing that.
Yeah, by a little bit. By a little bit.
It'll certainly take a bit.
Yeah,
Time.
it cuts a couple of eons off the time to do it. Look what they're really saying. Think about it just in an intuitive sense. You're saying, if I took the area under the curve of f of x, well, what am I multiplying by? 1 over b minus a.
1 over the length. Yeah, that's it. Yeah.
So I'm just chopping it up in little chunks. Right. If you start thinking of rectangles again, you're saying, well, each one of those f of x's for the rectangles is what it's talking about. Well, let's see what we do here. Let's find that average. So our function is 3x squared minus 2x. And the interval we're talking about is 1 to 4. If we don't have an interval, then this doesn't make any sense, right? So the first thing I'm going to do is integrate. I'll label this first.
On the weird squiggly thing, be on top or be on the bottom?
Top.
Okay, next.
The integral sign? Yeah. So I'm just finding out what b minus a is. And it's just 3. So then I'm going to integrate over that interval from 1 to 4. And notice what I put out front, 1/3. Well, that's 1 over b minus a.
Okay, let's see, that's x cubed minus x squared. I think. Yeah.
Good call. So there it is in terms of variables. And my 3's cancel, and my 2's cancel. And like the man said, it's just going to give us this. So every place I see an x, I'm going to put a 4. And then I'm going to subtract from that. Every place I see an x, I'm going to put a 1.
64 minus.
Am I going too fast? We're just down to arithmetic now. Good. That's just arithmetic, order of operations kind of thing. So I've got 1/3 just times 48, which gives me 16. Because the 1 minus 1 just goes to 0. Now, what does that mean?
Where did we get the 1/3?
It was 1 over b minus a.
Yeah, I remember that.
What does that mean? 16.
That means
If I took that function with all of its twists and turns, the average value of f of x is 16. Okay, so there's the average idea. Okay, this one I think is the weirdest part of the notes, although it's going to look really simple when we get to working a problem. So I've got, now notice they're talking about big F out here, right? That's the antiderivative of this thing, going from 0 to pi of cosine t dt. So notice I've got t and dt here, not x and dx. Because why? X is one of my limits of integration. Look up here. Don't let this get by you. We haven't seen one like that. Now, what could we do? Well, like the notes say, you could plug in 0 for x. Well, that'd be pretty easy. The area of that would just be 0, right? And then we could plug in each of these individual values. And so we could go through the whole integration process, really 4 times, not counting the 0, to get those answers. Or we could look at this as an accumulation function. And I'll show you what I mean by that in just a second. These accumulation functions pop up all over the place. Look, I put some examples of them here. Energy, distance, work. Looks a whole lot like physics.
number of equals.
So many of those things. Now the last one's not, but it doesn't have to be physics. But look how many accumulation functions are in physics. So here's a graphic idea of what an accumulation function looks like. Look at the top. Pretend like I'm traveling at a certain speed, a certain rate, a certain velocity in this case, and I'm going to do that for a certain amount of time. Well, think of x. I just put one specific x here. Think of x starting over here at the left and going to the right. As it does, what's it doing? It's accumulating area. Well, what's area representing here? Distance. And you go, well, no offense, laddie, but any fool would know that the longer you go at a certain speed, yeah, the thing is, the speed's not certain. It's varying. It's not like I drive 60 miles an hour for 4 hours. How far did I go?
So is the graph noting how fast you're going at each individual hour and half hour? And
At each individual point. Yeah. They just marked it in half hours and hours.
It's not accumulating how many miles you're going.
Yes, it is. The area under the curve is an accumulation of how many miles you've gone.
The line itself isn't just miles.
No. The line itself isn't, but the part I colored gray is. Okay, that's an accumulation function. If I moved x just one tiny little bit to the right,
the area would
increase And I could get the difference in those areas, couldn't I?
Yes.
From x to x plus delta x. Yeah. I could. And yeah, I know it. And if I call that delta x h, we could go all the way back to that, difference quotient kind of thing. But I could do that. If x came out here to 3, then I could get the difference of where it is now to 3, and that would be the difference in the areas. And I could start thinking, okay, well, we could get limits involved here. What you're looking at on top, to me, is the first fundamental rule of calculus. It means x is an accumulation of areas, or the point x, as it moves from left to right, is accumulating area. Look at the bottom.
That's a whole 5 hours.
That's a definite integral there, isn't it? It says, as you go from 0 to 5, there's your area. And so x will get replaced with a 5 up here. See? At any point along the way, say x stopped at 3.5, then the x up here would stop at 3.5. It's an accumulation of area.
So I'm noticing that that's marked with S of t. Where you plug that in the equation?
S of t is a location. All right. Okay, so let's see how that ties into. Here's the really weird part. They're calling this the second fundamental theorem of calculus, but really to me it's the first, because you're saying this is a general case as you're going from 0 to x. It's saying if you took the derivative of that integral, it's just f of x. Now remember, that integral has an antiderivative, big F. And we could go into the reasons why this works if you're interested. But it's saying, if you took that integral from 0 to x, that accumulation function, and evaluated it, got its derivative, that what you'd end up with is just f of x. And you have to think of it like this. I will say this much. John, don't let me lose you. These are functions of something. These are functions of x, not t. Right? I'm integrating over functions of x, but it's an f of t. So I would be taking the antiderivative of functions here to do it. Okay, all right. Let's work one. Now, look at this. And on a quiz or a test, I wouldn't make anything harder than this. They can get more elaborate, but I'm not going to do that, because it's the only time it's mentioned in the notes. I want to find the derivative of this and evaluate it. Now, can we get right now where we are in our calculus careers, can I get an antiderivative for the square root of t squared plus 1? No. I'm missing something. What would need to be here between that square root and the dt? Chain rule. I'd need a 2t out here.
That was what I was talking about on the notes. When he pointed at the thing, he was like, you can only do this if you add 2t. Remember?
Yeah.
That's the thing I was saying.
Yeah. Now, if I had this radical times 2t dt, then I could go, oh, chain rule, backwards. But I don't have a t sitting out. If I just had t, could I do it? Yeah. I could multiply by 2 in here and then multiply by half out there. So if I just had a stinking t, I could do it. But I don't. So right now, where we are in this class, we can't evaluate that. In chapter 5, we will be able to.
So, but why do we even need to? Can't we just tell from based on the top thing that the answer is square root of x squared plus 1?
It is, based on the top thing. That's what the notes are trying to get across to you. Based on this theorem up here, the answer is just if of x, well, what's that function with x plugged in? That. You're done. Now, it can get more complicated. We're not going to go there. But what if this was x squared up there?
Then
Would it be x to the 4th plus 1?
Then you got to get the chain rule involved. Okay. At that point, if it was x squared up there, then this would be x squared plus 1 times what? 2x. It gets weird. But we're going to leave it at that. All right. Last little area here. If we integrate from one end of an interval to the other, that's going to give us the net change. That can be positive or negative. It's net.
Okay, yeah.
And we've seen an example of that before. If I make $50,000 and I spend $51,000, the net change in my bank account is negative $1,000. That's his whole idea here. So let's look at number 4. Okay, F prime is the rate of change. So capital F without the prime would be the antiderivative. That's what we're doing here. That's what that fundamental theorem of calculus told us we could do. Okay? So here's how we're going to work it. I put my function of t in there. And now then, they're telling us t goes from 0 to 60, but that's not what they're asking us. I don't want from 0 to 60 minutes. I just want from 0 to 20. So I'm just integrating part of that. Okay, so I get the antiderivative. And I'm going to evaluate that from 0 to 20. So every place I see a t, I'm going to put 20.
15 times 20 is 3,600. Yeah, 3,600.
Now notice, for the 0 part, I've got 180t. So 180 times 0, 0. 3 times t squared, okay, 0. So that's why I've got a 0 out here on the right. So now I'm just multiplying. Like the man said, 3,600 plus 600. If I plugged a 0 into 180t, I'd get 0. If I plug a 0 into 3t squared. So I've got a net change of 4,200 liters. Did that tell us what we started at? How many liters were in this tank to start with? 0. No. 0 is the time. So we didn't know how many liters we started with. We don't care. It's just wanting to know what's the net change in that tank. Well, we added 4,200 liters to it.
Wouldn't it be negative 4,200 because the tank can only be empty?
Where does it say that?
Well, I mean, never mind. I'm sorry. I was thinking at the clock.
There are calculus problems that will say a tank is being filled at this rate and water's running out the bottom of it at this rate. What's the net change?
No,
And then you've got
Do
two
the same
integrals.
thing where you take both equations and then subtract.
And on some of them, On some of them, it'll be if the water's or whatever it is not running out as fast as it's being put in, at what time will the tank run over? And if it's running out faster than you're putting it in, yeah, those get interesting. Those get interesting.
Did we do that in college algebra?
We did work-related problems. That might be what you're thinking of. Okay, net change. All right. So we got a velocity problem here. S of t is the position function. If we get the derivative of that, we've got a velocity, right? We've seen that before. So they're assuming that we have gotten the derivative of S of t. They're calling it S prime of t over there on the left. This is the same as the velocity. If I want to integrate going from A to B, then the S's out here are technically the position functions, right? Evaluated there. Does that make sense? So the definite integral going from A to B, whatever those numbers are, gives us the net change. Okay, now think about that. If I took 4 steps this direction and then turned around and went back 5 steps this direction,
Net change is 0.
net change is -1. If I started at 0 and just kept on going that way, the net change would be however many steps I took. So if I took 15 steps to the left and then 15 steps to the right, I'm back where I started, so the net change would be 0. Okay, keep that in mind. That's one kind of problem. Then look down here at the total distance. If I took 15 steps to the right and then turned around and took 15 steps to the left, the net change is 0, but the total distance is 30. So don't confuse those. And can we use calculus to get the total distance? Well, yeah. Look what it tells us to do. We have to figure out where that area would be negative and take the absolute value of it. Where have we seen that before? I'm glad you asked. Right here. Remember this little problem? What did we see in this? We integrated it doing what? Using the limits. This was 4.3. And what did we find out? We got a -3, if I remember right, for the area. Why? Well, because this part over here was -12. And this part was 9. So the net change would be -3, and that's what we found because we integrated over the whole thing. What's this telling us? Well, decide where it's negative and then just take the absolute value. So what's the total here then? 21. And that's what this is talking about back here. The total distance in this case. All right, so let's work one. We got a particle moving along the line, and they're telling us the velocity that it's going at. That's kind of a complex formula. And t is in seconds. What's the displacement? Now then, that means net change. Could it sometime it be going in a negative direction? Possibly. So to get just the net change, all I have to do is integrate that, right? And it'll figure it out for me. So I'm putting my v of t, as it were, in an integral, and I'm integrating from 1 to 5, because that's what it says to do. As t goes from 1 to 5, what are we looking at here? Now remember, we're getting the antiderivative of a velocity. The antiderivative of a velocity is a position. Okay, I get the antiderivative. I'm going to evaluate that from 1 to 5. So that means every place I see a t, I'm going to plug in 5. Every place I see, and then I'm going to get those 4 terms. And then I'm going to go back and subtract the same thing by plugging a 1 in there.
We had a question like this on the test. Would you let us use calculators?
Sure. So here's what I did.
Dang.
Where are you going to mess up? You're going to forget to distribute this negative sign in between them into all of these terms. That's an easy place to mess up. I've done it a bunch. The squiggly line means I figured it out for you. Yeah, we could take up class time and do that, but here's what you get. Not bad. What does that mean? That means the net change from where we started at 1 to 5 is 32 thirds. What are we talking about here? It never gives us units, does it? Whatever units. So we're talking about feet, be 32 thirds feet, so that'd be what, 10 and 2/3 feet? No, not for displacement. Because you're saying, how far is it away from where it originally started? It's 10 and 2/3 feet in the positive direction from where it started. You realize that people with basically slide rules and big brains using calculus got us to the moon and back? Yeah, well, that's pretty amazing. Do you believe in Bigfoot? Okay. All right. Okay, let's look at B before this disintegrates into, oh yeah, well you're stupid. No, you're stupid. Come on. All right, so let's do part B. To do that, I have to know where this thing goes negative. Because now I want the total area. So I factor it. How can I factor it? Where would you start? You would use that PQ idea where you get all the factors of 20. Those are your P's, so it'd be what? 1, 2, 4, 5, 10, 20. And then you're going to, put, yeah. And so then you'd pick one of those and you'd do synthetic division till you hit one that came out with a 0 remainder, and that's one of your factors. Well, that's what I did. I actually did that.
Give me a second.
Yeah, sure.
So, 32/3, that's the output of the first equation. Why are we doing the next?
Because part B says what's the total distance traveled. That's including the negative.
Oh, yeah.
But treating the negative as a positive, in other words.
So
That's the roots of the original.
I found the rational roots. And so you start with, it's always good to start with ones. So what I did was synthetic division, and I divided 1 into this. And I'm trying to remember what I got. I got, well, t minus 1, but then I ended up with what's left over is a quadratic. So then I just factored it with the AC method. And I got these two. That's what you'd have to do.
Are we going to not do it on a number line and find a positive and a negative?
We don't even have to do that. These are my roots, right? So kind of on a number line. But we don't have to actually graph it. Because look, to the left of 1, what would I have? If I'm to the left of 1, let's just say 0. For my first term here, my first factor, I'd have what? A positive or negative? Negative times a negative. So there's a positive times a negative.
Oh, negative.
So I know that to the left of 1, this thing's heading down. It's going to be in a negative direction, this function, right? So here's what I'm saying. If I pick 0 and just look at my factors, 0 minus 1 would be negative, 0 minus 4 would be negative, 0 minus 5 would be negative. So I've got 3 negatives multiplied together, boom, 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 gives me a negative. So I know my function, if I graphed it, is as I approach negative infinity, the end behavior is going to be negative.
But does that comment on anything between 1, 4, and 5?
Oh, I'm glad you asked. So what I'm going to pick a number between 1 and 4. So I'll pick 2. Plug a 2 in. As long as it's between 1 and 4, it doesn't matter. You could put 3. So if I put 2 here, 2 minus 1, positive. Negative. So I got a positive times 2 negatives, positive.
Wait. Positive, negative. Wouldn't 2 minus 5 be negative?
2 negatives multiplied together give me a positive times a positive. Okay, so I know it's coming from negative infinity. It's coming up. It turns positive. Means it crosses the x-axis. We don't have to do any of the first derivative tests or anything like that here. I just want to know where it's negative. And so it's positive from 1 to 4. And so then I pick a number between 4 and 5. Well, I pick 4.5. If I don't have to do the actual math. If I put 4.5 in my first factor, I'd have positive, positive, negative. So I picked a number bigger than 5. If I put a 6 in all of those, they're all positive. So I know that it's going to go up. So, and Jacob Joseph might have been saying this, my only negative area here is going to be between 4 and 5. So I could just kind of quick sketch my little curve there. So what would I do? I could split this into 2 parts, integrate from 1 to 4, and then integrate from 4 to 5, realizing that that's going to be a negative value. So I do this. That's from 1 to 4. I know I can treat that as all positive because that's what my graph is saying. And then I'm going to say minus from 4 to 5. Because I know if I integrate from 4 to 5, I'm going to get a negative result because that's a negative. That's below the x-axis. So in effect, I've taken the absolute value of this area between 4 and 5 just by multiplying by negative. Well, that was from 1 to 5. We're going from 1 to 4. I'm glad you said that. On this one, I'm going from 1 to 4 because I know that's my positive part. And this goes back to a theorem that says, oh, you can split these things apart if you want to. Well, in this case, we do. And so we don't really need to work that out. That's how you would work it. It'd just be hoping you don't miss a sign someplace. Forget to put a denominator when you should. Little things like that. Little algebraic things. And so here's an actual graph of that. Well, I figured it out. It's 71 over 6 feet. Again, that's taking the area from 1 to 4 and adding it to the absolute value of that's those 2 areas pieced together. Notice that's quite a bit different from the net change.
Well, a question like this, similar length beyond test.
Mm-hmm. This was not bad. I mean, it's got a lot of. I wouldn't put that. I wouldn't put that many terms.
No, I mean, like, would this many terms?
No.
Okay.
No. If you can do it for 2 terms, you can do it for 8. So there's no point.